let's get into your background a little bit more in depth. I wanted to know, like, first, how you got interested in statistics and SEM and how it fits into your social science background. Like, why do social scientists care about these things? And if you can expand a little bit on that.
Sure. Yeah. So psychology, especially, has and other social sciences too, has to deal with a lot of constructs that are not super well defined. And so psychologists and also other social scientists are super anxious about like their measurement. And so how can we assure reliability of the measurements and validity of the measurements? So do we measure what we want to measure? Do we measure it reliably? Is there a lot of measurement error in the measurements when you measure, for example, intelligence or extroversion or well-being or something like that? Those are all vaguely defined constructs. And so structural equation models offer a tool to address issues of reliability and validity because they offer measurement models where you can check on those things. And so you can find out how reliable the measurements are. You can correct for measurement error, and you can also look into the validity of the measurements. And so therefore, that's what got me interested in that. So this the idea of using latent variables to correct for measurement error and how to do this properly, and that's particularly important in regard to causal inference studies because they are longitudinal. And so you want to make sure that when you have changes over time, that those changes over time are not due to measurement error, so that they don't just reflect spurious or random fluctuations in your measurements, but that those changes that you see over time, that they correspond to true changes. And so with structural equation models, we can separate measurement error from true inter-individual differences and also true inter-individual differences in change across time. So we can look at true change, for example, with growth curve models, with latent change score models, and that is a very helpful tool, therefore, in areas where you have a lot of measurement error or you think you might have measurement error, like in psychology.
Like a really at a simple level. So let's say someone never heard about structural equation models. Um, so basically, a structural equation model is a way to describe relationships between a number of variables. So a very simple one, you would just have two variables and you want to understand how one impacts the other. But obviously, in that case, it's very simple. But what is interesting is you can make like a more complex network of relationships, and you can model them very precisely, and you can add, like you said, latent variables, which are variables that are not directly observed, but that we measure using some proxies. I guess we can call it like that. We can add time components, and these models, they often resemble directic acyclic graphs or DAGs that my audience that are more familiar with causal inference methods of Judea-Pearl and all those people. And they not only resemble them superficially, but there are some like deep connections to certain aspects. Even if you read some of the causal inference literature, they talk about structural equation models without necessarily having the same concerns as psychologists or social scientists focus on, but they call some of these models structural equation models, and the reason is not trivial. It's because there is a lot of overlap. I wanted next to jump into like what are the good and bad of structural equation models. Like, so we say they're useful, they can help for measurement error, they can be super flexible, they can model many different things. But in your experience, like maybe if you could tell us what are some things that came out really good that you saw, and some things that turned out really bad, or some common misconceptions or some common mistakes that the people should be wary about when if they want to use these models in their work.
Yeah, so like you said, they're essentially like more complex versions or more general versions of regression models or path models where you have latent variables and multiple indicators. And so with this complexity comes the tendency to misspecify models because there are many ways in which structural equation models can be wrong. And one of the strengths of them is that they can be tested against the data. So most structural equation models will be over-identified, which means that they place testable restrictions on the covariance and or mean structure of the variables, for example, by setting certain paths implicitly or explicitly to 0. So you can test them with model fit tests, but then as the model grows larger, there are many ways in which a model could be wrong. And often they are wrong, and people accept them nonetheless. And they'll say, oh, they're an approximately okay fit. And so that can come with bias. So if you accept an incorrect model that doesn't really fit your data, then it's like wishful thinking a little bit. So the effects that are in the model may be incorrect, may be biased. And you have the same problems as in regression and path analysis and mediation analysis when you have omitted variables. Also, then it can be biased. So it's not per se a causal model, but it makes causal assumptions, and those may be right or wrong. People often apply structural equation models, at least in my field in psychology, to cross-sectional data, which doesn't allow you to say anything about causality really. So if you have measured all the variables at the same time point, and there's no experimental manipulation of anything, you don't fulfill the criteria of temporal precedence or necessarily control of all potential confounding variables. So you have issues there. And so that this is what I often see, is that people try to overcome flawed design or flawed measurement by fitting ever more complex structural equation models, and they think with fancy statistics they can mitigate the design problems, and that's really not the case. So structural equation models work great when you also have a great design and you have great measurement, and it can help you overcome some of the measurement error problems if you have random measurement error. However, it can't overcome fundamentally flawed research designs. And so people oftentimes draw conclusions from these models that are not warranted. So there are many also instances where an equivalent model is present. So you could have the same implied data structure, so a model that fits equally well, but that makes different causal assumptions, and it would fit equally well or better. So you can never prove with a structural equation model that your causal assumptions are correct. You can only falsify models that are incorrect. So if the model fit test says that the model doesn't fit, then that rejects your hypotheses. Or if you find that the paths that you hypothesized are 0 or near 0, then that can falsify your assumptions, but you could never prove that something is causal. And that's something that many people misunderstand. So they fit a structural equation model, and then they think if it fits well, and if the paths are significant, then that proves the causal assumptions. And that's really a mistake to think that, in particular when you have cross-sectional non-experimental data.
I think this is something we see a lot in statistics, right? Where we think that added complexity makes things better, but usually it makes things more brittle. It's like there's more chance of your structure will fall and tip over because you've made it very complex. If you use a simple model, you have maybe less flexibility, but it's easier to control. And I think this is something I see with structural equation models as well, is like in a sense it's like easy to make things very complicated. And like you say, this does not remedy all the problems with the data, like the basic concerns we should have, like how did we collect the data, what is the design, what is the temporal aspect. And the other thing that you said that I found really interesting is about confounding and causality and structures. So usually we see researchers who they take, like you say, a structural equation model, and they use like a test of fit. And if the test is not rejected, they say, oh, well, my model is good. But It does not mean the data is actually generated according to the structure you postulate in the model. It just means that we don't have a data that's far enough to reject it, and it's dependent on the sample size. So if you have a small sample, you'll be less likely to reject a test just by definition. Something to be careful with, right? If you just base all your decisions on strict hypothesis or statistical tests without thinking about how this data came about, what you're trying to do, and what are the design aspects you could implement to make the inference more robust, you're going to just end up with spaghetti soup of numbers, and it's not really going to tell you much. And I think this is something we see a lot of in the literature. The structural model you put in place is embodying your causal assumptions. It's not proving your causal assumptions. It's assuming they are true and giving you statistical estimates based on that. But you need more than just the statistics to understand. Does it make sense here to claim causality for an effect I'm interested in, or for a mediation analysis? I want to know if you just postulate a model and you assume there's a mediating effect and you estimate the coefficients and you say, oh, there we go, there's a mediating effect. Well, you assumed it beforehand, and you kind of need to be careful because there could be omitted variables, there could be correlation in the errors, or all the statistical pitfalls just get amplified by the complexity of the model. Next, I wanted to know, like, in your experience, how do researchers use, like, what are some ways researchers use these models? How do they decide, okay, I'm going to do a project and I'm going to use a structural equation model, and what tools do they have at their disposal to do this?
Well, ideally, they would make that decision based on whether they need to make adjustments for measurement error. I think that's really the main reason to use structural equation models is when you have measurement error in your data, so you have less than perfect reliability and you have multiple indicators at your disposal, and so you want to correct for error so that the structural relationships will be estimated with less bias, because we know from regression analysis that one assumption of regression analysis is that the predictors are measured without error, which in psychology is never true. So the X variables, they will certainly contain, most of them will contain some amount of measurement error, especially when you have questionnaire scores or test scores or something like that. And so then if you don't correct for error, then the coefficients in the regression model can be biased, the standard errors can be biased, the inference, statistical inference can be biased, so meaning tests of significance. And so to correct for that, people use structural equation models. And then also, because they have more flexibility over regression analysis, they are multivariate, so they can use multiple outcome variables, they can have mediating variables, moderating variables, they can be fit longitudinally, they can be fit with multiple groups, they can be fit to multi-level data. If you have hierarchical data, we can use multi-level SEM. And so they are very, very flexible. And that's a reason also why people use them. And so hopefully that would be the reason. Sometimes I think that some reason is to impress reviewers. So some people will fit a fancy structural equation model because they think then they have a better chance of publishing their results. And that really shouldn't be the reason to fit those sorts of models, but it should be to improve on your outcomes, meaning correct for unreliability and fit the most flexible possible statistical model that will give you a good answer to your questions. And then there's a variety of commercial and free packages now available to fit these models. So for example, there's MPLUS, there's AMOS, LISREL, EQS, those are commercial programs. And then within the R statistical environment, there is lavaan, which is very frequently used for fitting structural equation models, the lavaan package. There's also a lavaan GUI now online where you don't even have to open R. You can just go and search for lavaan GUI, GUI, and then you can draw a path diagram, and it'll run your model from the path diagram that you draw online using the lavaan package in the background, and you don't even have to mess with syntax. So that is great. And then there's also OpenMX in R. as a package for fitting these models. So it's widely available now. Also, there are even like in point and click software, like JASP has JASP has basic capabilities for fitting confirmatory factor analysis, and also structural equation models using lavaan in the background. So there's a lot of tools available for fitting those.
What kind of measurement error would motivate the use of an SEM? Like just a very basic example from your field.
We use a lot of questionnaires. So for example, for measuring depression, so people get asked questions and they may just simply misunderstand the question, or it may not be clearly worded. Sometimes questionnaire items are kind of two parts. So for example, like an item could be like, I feel depressed and sad all the time. And then maybe people are unsure. Well, yeah, I kind of feel sad, but I don't know, is that depressed? So they're like unsure. Does both of them apply to them? And so also they may just, I don't know, just like when the data is being entered into a database and numerically coded, people might make errors entering the data. And so there's typically random noise associated with questionnaire items and also test items. So when you have an intelligence test, and a capable student may randomly make an error with a number series problem, even though they're capable enough to solve that item, but they just may randomly make a mistake. And so we have a lot of that. It's unlike physiological measures, like when you measure temperature, it tends to be more precise than measurement in the social sciences, where people have to read questions and answer to questions. And
yeah, because like in biology, like I work a lot with biologists. I mean, there is variability in measurement, right? So if I measure, I don't know, blood pressure 3 different times, I won't get maybe exactly the same reading, but that variability is maybe small compared to the variability I get from person to person. So either I use sort of a repeated measures design if I think it's important, or I just assume that my measurement is pretty accurate, and I'm pretty safe doing that. But I think in social science, or in the field like psychology, when you say like depression, I want to measure depression, like what does that really mean? Like to operationalize that variable and create a measurement scale for it is a whole process, I think, and the measurement itself has to be taken into account in the statistical analysis. And I think that's kind of what you're saying, right? Like the SEM is a way to help mitigate or help I guess model into the statistical analysis the fact that your measurements are maybe more variable. They may have mistakes related to them, or they might be subject to some sort of effects, like confounding effects. Like I know in psychology, there's like these rater effects, right? Depending on who does the measurement, there might be correlation between the measurements and things like that. So am I right in saying it like that?
yeah, so there are different aspects to reliability and validity. So typically in measurement theory, so what we use oftentimes in psychology is classical test theory, where measurement error is clearly defined, so to say, as random noise. So you have a true score, a person's true score. So if you could measure individuals' ability an infinite number of times with the same test, then there would be a distribution of the scores simply due to random noise. Not every measurement would be the same, and so you could just take the mean of that distribution. That would be the true score, so the best guess of that person's ability. And so then deviations from the true score, that's what's defined as measurement error. So that's one aspect that can be modeled in structural equation models, is random measurement error in the sense of classical test theory. And then also invalidity. So there's this issue of method effects, for example, like you mentioned, rater effects. When you have self-reports and other reports, they may not agree. So where is the true depression? Is it the self-report, or is it the other report that is better able to capture that? And so that can also be modeled with structural equation models that include multiple rater data, where we can look at convergent validity between different raters. And model method effects as well. And so there are all these sources of systematic and unsystematic error that maybe in other sciences don't exist, where it just is in physics, it's just pretty clear what you're measuring. In psychology, it's not always so clear what you're measuring. And so therefore, psychologists are so concerned with reliability and validity. And so confirmatory factor analysis and structural equation modeling offer ways to address that by using multiple indicators. So multiple items, which basically is for repeated measurement. So like you mentioned earlier, so in order to determine reliability, we need to measure the same thing multiple times. And so oftentimes we do this with multiple items or multiple tests. And then we can determine to which extent those different items or tests share the same variance, so to which extent they're correlated. And so that's then what allows us to define a latent variable. And so the higher the correlation between the measurements, the more reliable those measurements would be, and the more variance in the latent variable, meaning the more true score variance. And so the goal is to separate, first of all, true score variance, so reliable variance, from measurement error variance. And then the structural equation model works with the true score variance in the latent variable and uses that then to relate that latent variable to other variables, so that the coefficients, the path coefficients or regression coefficients among the latent variables are less biased than would be the coefficients if they were estimated between manifest or observed variables that are not corrected for measurement error. So a latent variable is basically a perfectly reliable version of the observed variable.
I imagine you see a lot of times like models that or analyses that leave you a bit dubious, like I'm not sure if I really trust this, because it's a complex technique, right? Have you seen like some example of some very nice results, like, oh, thanks to the structural equation model, we were able to measure something super interesting or do an interesting discovery or an interesting confirmation of a hypothesis? Do you have any idea that comes to mind?
For sure, yeah. So it can be very useful. Like, for example, in our work, we have often found interesting results of rater discrepancies. So, like I mentioned earlier, so a lot of my work in this area was on multi-rater or multi-informant data. And so it can be very insightful to find out to which extent different reporters converge on the same construct or not, and then why not. So you can also then try to examine why are there certain rater discrepancies. And what is also very useful is when you have longitudinal data, you can clearly separate out the true change over time from random error. So then you're sure, is there truly a change in that construct? So for example, did depression really go down as a result of therapy? Or was it just regression to the mean? You know, regression to the mean is influenced by measurement error in part. So measurement error makes regression to the mean worse. And so with structural equation models, we can at least rule out that part of regression to the mean that would be due to random measurement error. That's a great thing, I think, with these models. So in particular, when it comes to modeling changes over time, we can be more certain when we apply structural equation models that there was actually change and not just error that caused fluctuations in the measurements, because it can be clearly separated. So yeah, there are many applications that are great, I think, but there are also a lot of examples where it's not so great. And what I often find is that people are sometimes a little bit too lenient in terms of accepting models, where they're like, oh yeah, this fits fine, and they find indices that will support their model even when other indices clearly show now that you could do better. And so people often don't look at the diagnostics, because there's an overall chi-square test of model fit, and so when that test is significant, it means your model deviates significantly from your data, so your model is rejected. And then you should look at diagnostics. So you should look at what covariances in your data are not well explained. So usually that's what that means when the model doesn't fit, is that you have underfitted, so that there are relationships among variables that are not represented in the model, or residual relationships. And so then oftentimes people will ignore those and will say, oh yeah, this is fine, this fits well. And then we don't know how biased the results are, because then you still get results. Even for a misfitting, non-well-fitting model, you get your coefficients, you can report those, and you may interpret them, but it may not be correct. So they may be biased. One book that I really like and I always recommend it as an introduction is the book by Tenko Raykov and George Markolidis, A First Course in Structural Equation Modeling. This is a very well written, very non-mathematical book that you can read easily, and it also has software examples in it. So this is great to get started. And then also somewhat dated but still great is Ken Bolland's book on structural equations with latent variables. It's from 1989, but not a lot of things haven't really changed since then, so the basic idea is the same still. And also it has a pretty intense section on causality also, and how structural equation models relate to causality. So that's a good book. It's a little bit more advanced than the Tenko Raykov and Markolidis book, but it's still very readable. It's very well written. So those would be good starting points. And then there's also a book by David Kenny on correlation and causality. It's also dated 1979, but still applies. And you can actually download a PDF for free from the internet. So it's on ResearchGate and maybe other sources, the whole manuscript. And it's really a good starting point for the connection between structural equation models and causality. Also, we offer free courses on goQuantFish.com where you can get started with the software. So we have a free course, MPLUS for beginners, lavaan for beginners, where you can get acquainted with the software application. I show many software applications also on our YouTube channel, how to get started with MPLUS and lavaan, and so you can check that out as well.
Social sciences, it's very hard. Like, I cannot randomize someone to be depressed, and see what is the effect of that on another variable. Or I cannot necessarily always randomize someone to, I don't know, to follow a therapy. It might not be possible for different reasons to do that. So if depression is the outcome, well, you say, okay, I want to see the therapy effect. I cannot necessarily randomize someone to therapy. So I need other tools to take care of this. And the tools in this book, the Shadish, Cook, and Campbell, they are all related to design. It's not about statistics in this book. They talk about statistics, but they want to show that, according to them at least, you cannot correct a flawed design with statistics. And I think we both tend to agree with that.
Yeah, I mean, that's the issue with a structural equation model. They can be applied to experimental or non-experimental data. So you could apply them to purely observational data as well, or to quasi-experimental data. And so there's multi-group structural equation modeling where you can compare groups. And it's actually very powerful because you can also test measurement invariance or measurement equivalence for different groups to make sure that the measurement scales, for example, work the same across different cultures when you do cross-cultural comparisons. Rather than just simply assuming that. So when we do that with, for example, an analysis of variance, we compare different countries, then we just simply assume that the measurements work the same way in those different cultures. And with SEM, we can actually test that. So that's another advantage for group comparisons that SEM has.
Yeah.
But yeah, I mean, it's clearly true what you said, is that you need to keep in mind that only because you fit in SEM doesn't mean that all of a sudden you get a causal effect at the end. It's more complicated than that. So if you cannot randomize, or you have only observational correlational data, then your model may be, the model that you accept may be a model that is one possibility. So it may be one thing that could be true, but there could be other models that maybe make different assumptions and that fit the same or better. And so that's really something that people need to keep in mind.
Yeah. In PhD level research, where complex models often involve multiple latent factors with more than 10 indicators each, how can one effectively manage and resolve estimation errors, such as model misspecification or Haywood cases, when using MPLUS for analysis?
Yeah, great question. So first of all, having more indicators per factor is actually beneficial as long as those indicators are good indicators, meaning if the indicators are unidimensional, it's better to have 10 of them than 2 for estimation. So it actually helps because they provide more information for estimating the latent variable. So it's actually not a bad thing to have more indicators. However, usually we don't have 10 great indicators. So maybe we have 3 great indicators, but not 10. So usually then you get multidimensionality. So you have the problem that those 10 indicators measure more than one factor. So you have correlated errors and stuff like that. And so then my personal position on that is that it's better to have 3 or maybe 4 or maybe even 2 good indicators that are unidimensional and are good, strong indicators of that latent variable than it would be to have 10 or 20. So I would then recommend selecting the best ones and getting rid of the ones that are not so good, because it's really only beneficial to have many indicators when the indicators are good, otherwise not. And so then you shouldn't get Haywood cases if you have 3 or 4 good indicators. I mean, it's more common when you have only 2 indicators. It's also more common when you have a smaller sample size, but it would not be common with many indicators if those indicators were good. So if they're good indicators, then it actually helps with the estimation.
Great. Thanks for sharing.
But it's a large sample technique. So we should also mention that maybe,
Yeah.
Justin, that SEM is not for n equals 50. So it's like it's a large sample technique that requires typically 200, 300, 400 cases to work really well.
Okay. Thanks for sharing. So we have still quite a few questions. Keep them coming. If we don't have time to do them all live, we'll answer after in the comments. But okay, so the next one on YouTube from Yanja. Thank you for the live event. Could you please talk about multi-level CFA? When do we need to use multi-level CFA? Thank you.
Sure. So when you have hierarchical data, so for example, when you have high school students nested within classrooms, or when you have employees nested within companies or individuals nested within therapy groups. So when you have a nested clustered data structure, then you have the same issue that you would also have in regression analysis, where your tests of significance and standard errors could be incorrect if you don't adjust for clustering, because you have dependencies in the data that are created by the nested structure. So individuals who are in the same classroom tend to be more similar to one another. And so multi-level CFA and multi-level structural equation modeling can be used to address the hierarchical nature of the data. And then also it can be used to test hypotheses at different levels. So you could have, for example, a multi-level mediation model where the mediator is at level 2 or another variable is at level 1. So you can model influences at different levels, which may be interested. For example, when you look at schools, some of the relevant variables may be at the classroom level or at the school district level, and some other variables may be at the individual level. And so you can then look at combinations of that and do multi-level mediation analyses, for example, and have cross-level interactions. But one thing to mention is that that requires really large samples. So then you have to also have a substantial sample size at the cluster level, meaning at the group level, for that to work well. And as a really rough rule of thumb, you need to have at least 100 clusters for multi-level SEM and multi-level CFA with latent variables to work well. For multi-level path analysis with only observed variables, it may be lower. So you may get away with fewer than 100 clusters.
So this is from David. You previously mentioned issues related to overfitting or using models to fix design flaws. Lately, I've been thinking that many of these problems stem from a lack of understanding of the philosophy behind inferential statistics and how theory informs and guides data analysis. Would you consider that pre-registration, when accompanied by a thorough theoretical framework and a strong empirical empirical background in the area of study are essential for being able to pre-specify a model before testing it. What was your experience? What has your experience been with this? So that was a big one, but I don't know.
So I'm not exactly sure I understand. So whether it's good to pre-register a study before doing it?
Yeah, basically, how can you pre-specify your model before testing it?
Yeah, I mean, you totally can do that because it's a confirmatory approach. So you're supposed to do that. So you're supposed to have a theoretical model that you specify before you look at your data. So otherwise you couldn't test it. If you looked at your data first and then developed the model, then it's not confirmatory. And so SEM is really a confirmatory technique, or supposed to be. But the problem is that people often, their models don't fit. So they have an a priori model that they come up with before they look at their data, but then they fit it and then it doesn't fit. And then they don't want to throw their data away, which is understandable. And then they start exploring and then they start to modify the model. And then sometimes people don't realize that once you modify your model, you can't really trust the tests of model fit anymore because they're already partially data driven. So they're informed by the data and you can't test with the same data what you have explored or derived from that data logically. And so that's a problem, that people modify models and then they sometimes don't report whether the model really was an a priori model or whether that was already a data driven model modification. So I think pre-registration can help if people are honest, but you could also run all your analyses and then pre-register. I mean, nobody would know. So I'm not sure that that really helps. People who want to cheat would still be able to cheat.
Yeah.
So,
Thanks
it's supposed to be a confirmatory technique where you test only your a priori specified models, and then you honestly report when none of those fit. You honestly report, we then modified the models, and then that has to be tested again using fresh data.